We're going to cover material for exam 3 on gases today, and as a review. And then the exam 3 will be next Monday, if not sooner. And we'll jump into chapter 6, thermochemistry, on that day. We'll also have a buffer day if we need it to finish thermochemistry, and then the review for that won't be till after the spring break. So let me share. I'm going to share the key for the chapter 5 review document, and we'll work off of that. Let's see, that's not what I meant to do. Let's go back. Share here. There we go. All right, I hope that's big enough. Let's start off slow and just review some general terms. What generally characterizes gases? Well, we know that gases are they don't hold their own shape, and they don't even hold their own volume. But there's generally less mass for the same volume as a liquid or gas, which means low density. So low density would be an answer. They're not high density. Their particles are not closely packed. No increase in volume when the temperature increases. That's false, as is E. If you increase or decrease the temperature of a gas, you get a considerable increase in volume, or decrease, as the case may be. So for that one, A is the only answer that works. They're just low density. How do we define pressure? Well, pressure is the force applied per unit area. And that means area. And this is force. So that's pressure. However, when we're discussing gases, sometimes the units for pressure are not force per unit area. Like the standard units measure would be newtons per square meter. That would be a standard for expressions of pressure in SI units. For gases, we sort of have to grandfather in some units of measure. One of which is the atmosphere. What's the pressure of 1 atmosphere? Well, it's that force bearing down on a unit area at sea level. We also have millimeters of mercury. That's not a typical quotient type expression for pressure. But for gases, millimeters of mercury refers to the height of the column that the gas will support, whether it's atmospheric measure like in a barometer, or it could be a manometer, where the pool of mercury is connected to some other source of gas. So you can measure the pressure of that gas using a barometer type instrument. Or it could be a sphygmomanometer, what otherwise known as a cuff. So you put the cuff on your arm, you pump it up, and you watch the pressure drop, and you listen for the Korotkov sounds. And you're just listening for 2 particular ones to give you the systolic and the diastolic blood pressure. So all of those are measured in millimeters of mercury. So back to the question. of all of these that are given, the only one that fits of these selections is force per unit area. And that is the basic definition of pressure. All right, SI unit of pressure, all right? The SI unit of pressure actually is not a quotient like that of force per unit area. It's the Pascal. The Pascal is convertible into force per unit area. In fact, 1 Pascal is newtons per square meter. Which of the following would represent the greatest pressure? Well, to do that, you've got to convert each one to a common unit so that you can compare them. Right? So, yeah, let's go ahead and do that. And there are 5 of them. Okay, we're going to use Henry Ford again. Assembly line. So we're going to do a similar procedure with different factors. So 0.680 atmospheres. My preference would be to convert them all to atmospheres, because we do have simple units of conversion for each one that'll make it atmospheres, and then you can compare them. So we'll leave that one alone. This one is 517 millimeters of mercury. So to convert that one, you need 760 is 1 atmosphere. That'll give you a value in atmospheres. This one, PSI, which is an abbreviation for pounds per square inch. So how many PSI in 1 atmosphere? Well, it's 14.69. Okay. Pascals, 62,106 pascals. That's a small a, excuse me. Now we need a conversion that'll make 1 atmosphere. And it's 101,000 something. 325 pascals in 1 atmosphere. And then our last one is inches of mercury. So how many inches of mercury in 1 atmosphere? Actually, it's 2992 inches of mercury in 1 atmosphere. Now we just need to do the calculations and find out everything in atmospheres and compare them. All right, 517 and 760. That's 0.680. 0.680. I think I can see where this is going. Um, 11.4. 14.69. Oh, no. I guess wrong. 776. 0.776. 62,106 and 101,325 divided into it is 613. And 14.1 divided by 29.92 is 471. Now, what's that? They give the answer C, 11.4. Oh, yeah, that's right. This was the biggest one. I thought for a second that we were going to have all of them the same way, the same numbers, but there was no selection for all the same. These happen to be the same, but that one is the biggest. So that's why the answer is C. Okay. All right. Let's see. Let's see if 5 is worth investigating. A glass column is filled with mercury and inverted in a pool of mercury. All right, so they're making a barometer. The mercury column stabilizes at a height of 729 millimeters above the pool of mercury. What's the pressure of the atmosphere? You just convert that to atmospheres. 729 divided by 760 is 0.959. So that's why the answer is C. Very simple conversion. Okay, so now I've got some of them marked that I want to be sure and hit. 6 is one of them. A local forecaster reports that the current barometric pressure is 30.4 inches of mercury. What's the current pressure in atmospheres? Well, we did one like that just a minute ago. How many inches of mercury is in an atmosphere? 29.92. Let me see, is that in your useful information? Let's see, yep, there it is. 2992 inches of mercury, 1 atmosphere. So we've got 30.4. 1.016. Rounded off, 1.02. That's right, only 3 significant figures because of this number right here. Okay. Let's go to 8. The tire pressure in an inner tube of a tire on a typical racing bike is held at a pressure of 112 psi. That's right. I used to have what they call 10-speed that I rode everywhere, and it had these little narrow tires. They weren't racing tires, but they were narrow. And apparently, the narrower the tire, the higher the pressure. And the pressure in those tires, I maintained at like 85 psi. It's really high, but you needed that for the tire to function properly. So at 112 psi, how many atmospheres is that? Well, psi, 1 atmosphere is 14.69. psi. That's 7.62 atmospheres. That's a lot of pressure. Now, if a tire like that blows, it'll make a loud bang, but there's not a whole lot of air in it, right? So the danger is not quite as bad as it may appear. 7 atmospheres, 7.5 atmospheres is a lot of pressure. It would only be a danger if that pressure were applied against a liquid. Like if your tire were partially filled with a liquid and it blew in such a way that there was a jet of liquid that came out of that hole. If that jet hit you, it would penetrate your skin. In fact, the hydraulic systems on the SR-71 Blackbird, that spy plane, are enormous pressures against the fluid in the hydraulic system. And people who worked around there were cautioned to watch out for any anomalies they may see, like little drips or weird sounds, if they didn't have the engines running, of course, because that fluid was not only pressurized, but it was hot. They heated it. And it was under such high pressure, if the pinhole link in one of the pipes was experienced, that jet of fluid would go right through you. And of course, it would kill you. Okay, so let's take a look at these laws and be sure we have them firmly in mind. Boyle's law, right? Boyle's law is the relationship of pressure and volume. Whenever you multiply pressure times volume, you get a constant value, all other things being equal. And by that I mean, if you've got pressure, volume, moles, and temperature, the four defining factors for a gas, then if we're studying pressure and volume variation, we have to hold moles and temperature constant. So the answer for that one's B. Avogadro's law. Which ones do we hold constant for Avogadro? Let's see, am I still on? Yeah, I'm still on camera. For Avogadro, we're relating volume and moles, these two. So pressure and temperature have to be held constant. Right? So in that case, Avogadro's law says that for when the moles goes up, the volume goes up. So whenever you have an inverse relationship, the product is a constant. Whenever you have a direct relationship, as one goes up, the other goes up, then it's the quotient that's equal to a constant. And then I think on the next page we got 11, Charles' law. Right. Charles' law relates volume and temperature. And these are different. So in order to study volume and temperature, you have to hold pressure and moles constant. Okay, let's see. Yeah, we're going to look at number 12 also. So when we consider a sample of helium gas in a container fitted with a piston, just like this picture. The piston is frictionless. That's hypothetical, right? Everything that touches anything else, you experience friction. I mean, even Teflon has a certain amount of friction, even though it's very low. So we want to take friction out of the picture. That's the idea here. This piston has a mass of 10 kilograms, so it's bearing down on a trapped gas in that cylinder. Which one of these, or how many of these, Roman numeral 1 through 4, how many of these processes will cause the piston to move away from the base and decrease the pressure of the gas? Okay. Now, it has to be both of those conditions, right? So for the piston to move away and the pressure to decrease, then heating up the cylinder, heating up the gas will not decrease the pressure. In fact, in the beginning, it'll increase the pressure until the piston moves up and we reach equilibrium again. And at that point, the pressure is stable. But in that new position, the pressure did not change. From the pressure before, the pressure would, well, let me take that back. No, the new position would actually be a higher pressure, but the volume would increase. Remove some of the helium from the container. Well, if you do that, by the way, what is the pressure on that cylinder? It's atmospheric plus 10 kilograms, or whatever force 10 kilograms applies, right? Kilograms is a mass, so it's not really a force measure. But we can, for illustrative purposes, we can say the force of the atmosphere plus 10 kilograms is the pressure on that cylinder. So if we heat it up, the pressure is going to be constant eventually. If we remove some of the helium from the cylinder, then the pressure will stay the same, but the piston will move toward the base, not away from the base. All right, so 1 and 2 are wrong. They're completely wrong. Turn the container on its side. All right, what would that do? Well, how is pressure applied in a container? Pressure in a container is applied in all directions. So the pressure of this gas in here is applied at a certain pressure. And if you turn the container on its side, what's the atmospheric pressure on that cylinder? It hasn't changed because pressure is every direction. But when we turn it on its side, now you don't have 10 kilograms bearing down. The 10 kilograms now on the side would be like this. There's your cylinder. And that's 10 kilograms. But which way is the 10 kilograms pushing now? It's pushing that way, toward the center of the Earth. So that 10 kilograms is not pushing against the gas anymore. So now, what was holding the gas down with 10 kilograms of mass plus atmosphere is not holding it down. So in that case, the piston is going to move up. And in fact, if there's enough pressure on that gas, it's going to move out of the cylinder and just open it up. So that turning the container on its side does decrease the force against the gas and allows the piston to expand, decreasing the pressure, because the only pressure on it now is 1 atmosphere. Okay. 4, decrease the pressure outside the container. Decreasing the pressure outside the container would do what? The piston moves away from the base and decreases the pressure of the gas. You know, that one should work also. So that tells me that that answer is wrong. I think Roman numeral 4 would also do it. If you decrease the pressure outside the container, sitting upright, right? Then there's less force against the gas and it moves up. And there's also less pressure on the outside, so the pressure on the inside moves up until they're balanced again. Okay, so 3 and 4 also work. That means the answer should be C, actually. So let me see if it'll accept my input while it's being shared. Okay, that worked. So actually 2 of these are right. 3 and 4. All right. Let's see, next on the agenda. Let's go to 15. Gaseous chlorine is held in 2 separate containers. Identical temperature, identical pressure. So the temperature and the pressure are held constant. 2 separate containers. The volume of container 1 is 1.3 liters. Okay. The volume in container 2, and it contains 6.7 moles of gas with 6.70 moles. And this has chlorine in it. And there's another container with chlorine also. 2 containers. Yep. The volume of container 2 is 2.33. How many moles are in that container? All right. What are we comparing? Volume and moles. That's Avogadro's law. So we would say that the volume of 1 divided by the moles of 1 equals the volume of 2 divided by the moles of 2, right? This is a before and after situation, except it's not really on the same cylinder. But Avogadro's law says they don't have to be the same. As long as these two conditions are held constant, then these variations can be compared between two different cylinders, actually. So what's V1? Well, V1 is this, right? 1.30 liters. What's N1? 6.70 moles. What's V2? V2 is 2.33 liters. And N2 is our unknown. Right? So now we can solve for our unknown. If this comes over here, then that divides into this, and that multiplies by that. I get 12.0 moles. Let's see, does that agree? Yeah, that agrees with the key anyway. Now, did we have to know that? Well, of course, to answer those previous questions, you know, what's Avogadro's law, you need to know that relationship. But when you're solving a problem, if you decide, and you know it's before, after, rather than state, then you can take the, just use the combined law. Okay, that's the combined law. And if you hold pressure and temperature constant, those terms drop out. And now you have V1 over N1 equals V2 over N2. Okay, so even though all that information is in the review document, in the useful information, and it will be available for the test, if you know this relationship, that's the only one you need to solve problems. Okay, that was 15. Let's see, skip to 18. There's 18. Okay. All right, body temperature is about 309 K. Is that right? 309 minus 273. And they're off by a degree. Body temperature, well, what we consider normal body temperature is 37 degrees C. That temperature is 36 degrees C. So that's probably pretty close. Most people, at least the way they measure temperatures now, with the infrared scanner or the temple rub or some other thing, even the thermometer under the tongue won't be core temperature. Core body temperature is 37 degrees, but places that you measure it, except for one, anal thermometer should give you an accurate core temperature measurement. So 36 is probably not far from the truth. On a cold day, what volume of air at 276 K must a person with a lung capacity of 2.2 liters breathe in to fill the lungs? Okay, how are we going to read this? This is before and after, right? So the temperature is changing from 309 to 276. Let me see. Yeah. So we've got a comparison of volume and temperature, which is Charles' law. The key here is to get the temperature and the volumes in the right position. Like which one's V1 and which one's V2, for instance, or which one's T1 or T2. So if we start at 309, okay, let's look at it this way. Here's a person's down into their lungs. I know it's a bad drawing. Okay, the temperature out here is 276. Okay. The temperature in here is going to be 309. The volume in here at that temperature is 2.2 liters. So how much of the air at that temperature must be drawn in to fill your lungs at that temperature? So when you draw in a certain volume here, it's going to expand as your body heats it up. So you could say this is V1, this is V1T1, or this is V1T1. Doesn't matter as long as you get them together in the right place. So if we say this one, the volume inside the body is 2.2 liters, and at that temperature is 309 K. The volume outside is our unknown, and the temperature outside is 276. Now, that was the real key, is to get those numbers in the right place. If you put them in the wrong place, you get the wrong answer. And if this is a well-made multiple choice set of answers, then the wrong answer is going to be in that set. So if you do it wrong, just because you see the answer there doesn't mean it's the right answer. So that's why I wanted to draw the picture, so I could get a clear idea of what belongs where. So now if we solve that equation, we'll say this divided by that times that. Uh, 1.97. 1.97 liters. Well, that's it. Let's see, is that one of my, yeah, it's B. B is the answer for that one. Okay. All right, let's see. 20. Let's look at 20. Okay. Oh, the balloon problem. Okay. You have two balloons, an orange balloon and a blue balloon. So we got orange and a blue. I didn't draw the balloons yet because I don't know what size they are. And I may still not know until I've looked at every part of the problem. The orange balloon is filled with neon. So this one has neon in it. And the blue balloon has argon. Okay. The orange balloon has twice the volume of the blue. Okay, now we're getting somewhere. This one has twice the volume of that one. So this one's going to be that size, and this one's going to be about that size. Right? So this one is the volume of the blue balloon. This one is the volume of the orange balloon. And what's their relationship? This one is twice the volume of that one. Okay? Which of the following best represents the mass ratio of neon to argon in the balloons. Okay, so what do we need to know? Well, we need to know if this is twice the volume of that one, what's the relationship between the two? The molar mass will help us, right? If we're talking about mass, we know that the number of moles here is twice the number of moles there. Avogadro says that. If this volume is twice that one, then the number of moles here is twice that one. Okay? So, the only way to get at the mass is to compare the molar mass of each one. Well, argon is about 40, approximately 40 grams per mole. And neon is about 20, I think. Yeah, 20 grams per mole. Okay? So, this one has the molar mass is about that rate. It takes twice as much of this to make that. But you've got twice as much over here as that. So what that tells me is that the mass of the orange balloon is equal to the mass of the blue balloon. We've increased the number of particles twice as much, but the particles are half the mass. Right? So it's inversely proportional. So the mass of the orange balloon is equal to the mass of the blue balloon. Okay? So that would be a 1-to-1 ratio to answer the question. All right, that was 20. Let's see. 20. Skip over to 29. 29. All right, so let me see if I can get there quicker like this. There's 29. Okay. All right. A gas sample is heated from minus 20 C to 57 degrees C. Let's just read through the problem first and see what kind of problem we've got. So we're increasing the temperature from minus 20 to 57, the gas sample. That tells me that you're not changing the number of moles. Moles are constant. And in that process, the volume is increased from 2 liters to 4.5 liters. If the initial pressure is 0.14 atmospheres, what's the final pressure? All right, so we're changing 2 different factors to find a third unknown. And it's before and after. You got a change in temperature, you got a change in volume. We want to know what the change in pressure is. So that being said, we can't use one of the simple laws because they're only comparing 2 factors. We need to use the combined law. All right. We already said that the number of moles didn't change. The gas sample is confined. We're not adding any moles to it. We're not taking any away. So that term drops out. Now we have this expression to go on. What we need to do is find out which one's the ones and which one's the twos. Right? So if we're going from minus 20 to 57, then temperature 1 is minus 20 degrees C. Temperature 2 is 57. Okay. Volume 1 is 2 liters. 0.00 liters. And volume 2 is, it ends at 4.5 liters. If the initial pressure is 0.14 atmospheres, initial pressure is 140 atmospheres. Now we want to know what this one is. There we go. All right, can we go now? Are we there yet? No, we're not there yet. We can use these values here as is. That's no problem. What we can't use as is temperature. Why? Because all relative temperature systems have negative values, like Fahrenheit, Celsius. Now, those are the only two we've studied, so they all have negative values possible. You can't have negative values in this type of calculation. You got to have positive values, which means that has to be changed to Kelvin. So we add 273. We add 273. Now we get a value here of 253 minus 20 and a plus 273. And this one is, let's see if I can do it in my head. 0, 13, 3, 330K. Now we can plug those values in. So let's see. Well, let's do it this way. Erase this one. And I'll use that as my model. So P1 is 0.14. I'm going to leave the units out just for space saving. V1 is 2 divided by T1, 253. I'll put the K in there for posterity. Okay, now we need P2 V2 over T2. P2 is our unknown, right? V2 is 4.5. Well, I said I wasn't going to do that, but I'm writing the force of habit. Write the units in. And then T2 is 330. Okay? So P2, the answer is going to be the product of these two times that one also, because it comes over here, divided by that one, and also then divided by that one. So 0.14, 2, 330, and then 253 divided and 4.5 divided. So I get, is that right? Did I make a mistake? 29. No, that's what it says. 0.081. 3 places. 811. Okay. So the pressure was 0.14 atmospheres. Now it's less, 0.08. So working these problems really is a matter of understanding where the values go. Because all of this, I mean, it's just a mess unless you read it and transfer the information to a different form where you can see the difference between one and the other. Okay, that was 29. 30. Let's look at 30. All right. Let's see. It's walking on me again. There we go. 30. A sample of oxygen gas, right? What would that be? That's oxygen gas. Diatomic, remember? Has a volume of 1.72 liters at 27 degrees Celsius and 800 torr. How many oxygen molecules does it contain? All right, what kind of problem is this? Is this a state function or a before and after? This is a state. We're only given single values for each of these terms: volume, temperature, pressure. And we're asked how many molecules, right? Which, to solve our problem, we have to we have to find the moles first. Then we can convert to molecules. So what's the formula that we're going to use for that one? Okay, and we're looking for moles. Okay, TD over RT. So what's the pressure? Well, now it's important that the units that we use match those that are in the constant, the universal gas constant, or the ideal gas constant, excuse me. So these values are, let's just write it over here, 0.08206 liter atmospheres per mole K. So the temperature has to be in K, right? 27 plus 273, which is 300, isn't it? Yeah, 300. Then the pressure has to be in atmospheres. Is it? No, it's 800 torr. So that's 800 divided by 760. And then volume is in liters. That's okay. All right. Now we can find out how many moles we have. Okay, I got this term. Now divide by 0.08206 and divide by 300. So I get 7.35. How many significant figures? 3. I'm going to keep a bunch because I don't want rounding errors. 7.354 times 10 to the minus 2 moles. Now we got to convert to molecules. So in 1 mole, we got 6.022. I had to stop for a minute. Times 10 to the 23rd molecules. Okay. So this times that will give us the number of molecules. It did say molecules, didn't it? Yeah, oxygen molecules. All right. What if it said atoms? Then we would have to multiply that answer by 2. Right? And if that question comes up and you don't know that this is diatomic, or you don't remember that, then you get the wrong answer. All right, 4.43 times 10 to the 22nd. And it looks like it's A. All right, that was 30. All right. So let's go to 37. This should be a quick answer. You just have to know this one. We've talked about it in class, but there it is, 37. Which conditions of pressure, temperature, and moles in are most ideal? Right? A gas will behave ideally if it approximates the ideal gas, which has a point volume, right? No volume for the gas molecules, and there's lots of distance, space, lots of space between them, and they don't interact. No interaction. So how do we increase the space, guarantee as little interaction as possible, and no volume? You try to get those molecules as far away from each other as possible, and for no interaction, you make them move as fast as you can. Because if they're moving fast, they have less time to interact if they do encounter one another. Right? So that means low pressure means lots of space between the molecules, because there are fewer molecules in the space, so they're farther apart from one another. It's like a room with where you're watching TV by yourself, and then on the weekend you have a party there with 20 people. Right? There's going to be a lot of interaction. Whereas if there's only one person in the room, there's no interaction. So low pressure, high temperature, get everybody moving fast, and low moles. As little gas as possible in there gives you an ideal behavior. So which one is that? Low pressure here, low pressure, high temperature, and low moles. I think in the lecture introduction of this material, I didn't mention low moles. So maybe that's why I picked this question, because I wanted to hit that point. Low pressure, high temperature, and low moles. Okay. Let's see. We're going to skip a little bit. There must be a lot of redundancy in here. I wouldn't have skipped them. How about 49? So let me turbocharge this thing. Get down to 49. Here we go. For which gas are the molecules diatomic? Molecules diatomic. Okay. Now, this is kind of a play on words. When we say diatomic element, we mean that the molecule of that element is composed of two atoms of the element. So any one of those diatomics, hydrogen, nitrogen, oxygen, fluorine, chlorine, bromine, iodine, those would all be diatomic molecules, right? So chlorine is a good fit here, right? Helium can't be it. See, the other way of interpreting it is if the compound is diatomic, it only has two atoms in it. So that one has 4, that one has 5, that one has 1. So I made it easy. The only one that's got 2 atoms in it is chlorine. Let's see. Let's go down to 52. I want to get some, oh good, I've got some graphs coming up. Graph interpretation. Students seem to have trouble with that. Learning the rote memory of laws and just facts seems to be something that most students are reasonably good at, but applying that information to a visual like a graph, is something that the students tend to have trouble with. Not all students, of course, but on average, it seems to be a problem. So we're going to hit one or two of those before the end of the day. Let's get 52 and 53 out of the way. Okay. The mass of 1.12 liters of gas Y at standard temperature and pressure is found to be 6.23 grams. The density of the gas is what? All right, okay. There's a lot of mystery in that one, it appears. First of all, what's STP? Right. It's not a gasoline treatment that you pour in your tank. STP is standard temperature and pressure. For gases, they're unique. Well, standard pressure is the same for any chemical reaction or any chemical study. Standard pressure is 1 atmosphere. Okay. Standard temperature, though, for gases is 0 degrees Celsius, or 273 K. Okay, so you need to know that. That's standard temperature and pressure. Now, under those conditions, we have a gas that is 1.12 liters in volume. Okay, and the mass is 6.23 grams. All right. So let me see if this is a trick question. It is a trick question. All this stuff in here is, there's a lot of blue smoke, right? We're just asking for the density of the gas. The standard temperature and pressure doesn't matter. If all it wants to know is the density, and it didn't change the conditions, if it said, what's the density at room temperature, 25 degrees Celsius, then we'd have a problem, because you'd have to find out what the volume is at that new temperature. But if this liters of gas at standard temperature and pressure is all you want and all you need, then we don't have to change it. So we just say the density is equal to mass per unit volume, which is 6.23 grams divided by 1.12 liters. Okay. And that means we can estimate, like one is about 6, between 5 and 6, right? So B is probably the answer here. Yeah, 5 and 6. If we had time, then I could invent a problem. So, we're going to take the same problem. And now the molar mass of the gas is what? Now we have a problem. Worthy of some brain power. What do you need to know to calculate the molar mass? You need to know the mass of the gas and the number of moles that represents. We know the mass right here. That mass is given. We know the volume. We know the temperature. We need to know the moles. What's the pressure? Pressure is 1 atmosphere. This is a state function. This is what it is right now. So, we need to know the number of moles. We got the mass already. We got to find the number of moles. So if we solve this for moles, we have N equals PV over RT. So the pressure is 1 atmosphere. The volume is 1.12 liters. R 0.08206. And temperature is 273. So now we can find out the number of moles. Let's see, 1.12 times 1, then 0.08206 divide, and 273 divide. So that's 5.00 times 10 to the minus 2. So molar mass, or molecular weight, I call it, is grams per number of moles. What did I say? 5 times 10 to the minus 2. All right. So we just take that number and divide it into 6.23. I get 125 grams per mole. That's C right there. Okay. What we needed to do was read the question backwards. What's the molar mass of the gas? What do you need to know to find the molar mass? You need to know the mass and the moles. We got the mass already. So find the moles of a gas. How do you find the moles of a gas? Do we have enough information? As a matter of fact, we do. We had volume, we had temperature, we had pressure. Plug it in the formula. There's only one unknown, moles. All right. Let's see. Next on the list is 56. That's got graph interpretation here. 56. There we go. Which is the best qualitative graph of pressure versus molar mass of a 1 gram sample? All right. If you have a 1 gram sample of gas, the moles will be constant. Right? Once you have that gram of gas and you don't substitute anything else for it, then that gram represents so many moles. So the 1 gram sample ratioed to the number of moles gives you a molar mass. All right. So this is not going to be as useful as I thought it would be. Actually, it's kind of a trick question. 56. Here we go. But I'm going to do it anyway. Okay. 56. So what are we looking for? We're looking for a plot of pressure versus molecular weight or molar mass. You know what? That's not a very good question. Because when you stand back and think of it, what effect does pressure have on molar mass? If you've got a 1 gram sample, the moles is constant. The moles are constant. So you would expect that the molar mass would not change with pressure. So that means that C would be the answer, right? If, as the pressure changes, what happens to the molar mass? Nothing. The molar mass is constant. All right, so that's a bad answer too. That should be C. And the explanation that I put in the worked problems is, as Shakespeare would say, much ado about nothing. that really means, I mean, mathematically it's correct the way I put it in here, but physically speaking, it's completely wrong. The molar mass does not change with pressure. Now, the density changes with pressure. That's true. But the molar mass does not change because it's moles per mass. Mass is not affected by pressure. Moles is not affected by pressure. As long as the sample is the same and doesn't change, 1 gram sample. So that's why C should be the answer for this one. I'm going to have to make a correction here. This should be C, and the graph should look like this. All right. Okay. So let's move to 61 next. There we go. Let's see if I need that space. All right. This is a good exercise. Let's read it first. We'll read it forward and then we'll read it backwards. 0.72 grams of liquid is vaporized at 110 degrees Celsius and 0.965 atmospheres. That much gas occupies a volume of 0.55559 liters. The empirical formula of the gas is CH2. What's the molecular formula? Okay, there's a lot in this problem. Read it backwards. Molecular formula. If we need to know the molecular formula from that empirical formula, we need to know that multiplier. All right. So what do we compare when we do that? We compare the molar masses. So we got to find the molar mass of the gas in order to compare it to the empirical mass, right? So the empirical mass is 12.01 plus 2.02, right? 2 hydrogens. So that would be 14.03 grams per mole, and this is empirical weight. There we go. Now, I'm trying to get a feel for where we're headed. We need to find the molar mass of the gas, right? So what do we need? Mass and moles, right? We have the mass, 0.72 grams. M equals 0.72 grams. All right. Now, how do we find the moles? Well, we're given a state situation. What is it right now? That means PV equals nRT. So PV equals nRT, N equals PV divided by RT. Do we have the information we need? Pressure. In atmospheres, 0.967. Yep. 0.967 atmospheres. How much volume does it occupy? 0.559 liters. That's the correct units. The gas constant. Okay. And temperature. 110 degrees centigrade, Celsius. We got to do something with that, don't we? 110 plus 273. is 383. Yeah, 383. Okay, so the number of moles is what? And 383. 1.720 times 10 to the minus 2. Moles. Okay, now we can calculate the molar mass. So the molecular weight of this gas is mass, here, divided by moles, equals 41.9. All right, compared to 14.03, is about 3. That's equal to our x. So 3 times this says C3H6. Okay, that's why the answer is C. That took a lot of work, which is why you have to be very methodical about your approach. So what is the question asking for? What do I need to know to answer the question? Then you go back to the problem and say, is the information there? Or can I get the information legally? On a test, that would mean all that useful information that I provide. That's legal to use. Okay, let me do a quick check and be sure. Yeah, okay. No new members have shown up, so we'll go ahead. Let's see. How about number 80? So let me turbocharge this thing. I just learned how to do that not too long ago. Okay. If M is the molar mass, big M, fair warning, this is going to test your memory for algebra and solving for unknowns. If big M is the molar mass, 80, I need to let that one rest. It's starting to get dim. Here we go. That's the molar mass. Okay. R is the gas constant, T is temperature, P is pressure. Which of the following expressions represents the density of a gas? Density equals what? Okay, that's what we're looking for. All right. So we've actually got 3 intersecting formulas here. Or is it formulae? Yeah, formulas. What's molar mass equal to? It's equal to moles. No, excuse me. It's equal to mass per mole. Okay. What is universal gas equation? And I'm looking at this term right here. So that's PV equals nRT. Now these two are linked by moles. What else do we need? For density, we need mass per unit volume. So now we have a need for volume right here. Right. So the linkage is this is linked to that, and that is linked to that. Okay? So we need an expression in terms of a substitution for mass and volume. Right. Well, actually, we're going to have this. If you look at your answers, there's no mass in there. It's just molar mass. Right? So we're going to have something. This has to go into this expression. Right? So what we're going to do is we're going to take this density density is equal to mass per unit volume. So we have to solve it for, we got to get rid of the mass. Yeah, we got to get rid of the mass. Actually, we need to solve this equation for mass. Equals dV. And then dV goes in right here. Okay, that gets rid of mass because we don't have mass anywhere in these answers. All right, so now we have D times V up here. How about this one? This one substitutes into this formula for N. So N equals PV over RT. And this goes right here. So now we have molar mass equals density times volume divided by, P, that's P. PV equals RT. PV over RT. Okay? Now, remember what happens with a fraction of a fraction. If you have a fraction in the denominator, then the denominator of the denominator is the numerator. So it just flips like that. So this now becomes dV times RT over PV. Okay? So the volumes cancel out. The rest of the terms stay, and now we solve for density because it said, what's the expression that represents density of the gas? So we solve for this term. That means this stays here. That one goes over here, right here. And this one comes to the numerator. Right? So it should be molar mass times pressure divided by RT. Molar mass times pressure divided by RT. It's this one right there. Okay? I know that was, we had to dance around the barn several times to get there. But it's a good mental exercise. Now, why would we want to know that? Well, if you have an experiment where you're trying to find the density of the gas, you know what gas it is, you know its molar mass, you can measure the temperature, you can measure the pressure, you can find out what the density of the gas is without directly measuring it, if you don't have a way to do that. This is simple. Then you only need two measurements. If you know the gas, its molecular weight, molar mass, then all you have to do is measure the pressure and temperature. And you've got its density. Okay, let's see. Yeah, I'm starting to run short of time. Let me see if I'm going to miss anything here. Yeah, I got a long way to go. So the lab tutorial, which normally takes place at right after class, 3:45. Might have to postpone that a little bit until I get finished with this. But if you leave early, you have to leave early, that's fine. If you want to come back at 3:45 for tutorial on the labs, then you'll have to sit there for a little while until I get finished with this, which is all right. There's a waiting room. Okay. Let's see. Okay. 81. Okay. One way to isolate metals from their ore is to react the metal oxide with carbon, as shown in the following reaction. So what does that actually do? Well, we haven't studied redox reactions yet, but what it does is it transfers electrons to the metal. Remember, when a metal and a nonmetal combine, the metal becomes the positive, or the cation, and the nonmetal becomes the negative, or the anion. So what we need to do is provide extra electrons, which is what the carbon does, so that the metal can be, we say, reduced and converted into the free metal. Okay, so if this is our reaction, 2 times MO, and that's the ratio, 1M to 1O, yields 2 metals and 1 carbon dioxide. Okay, that's the operating reaction. Okay, so we have 2 of these plus carbon yields 2 of these. Is that right? Yep. Plus CO2 gas. All right. Now what are we given? 34.08 grams of the metal oxide react with excess carbon, and 4.37 liters of CO2 are formed at 100 degrees centigrade Celsius and 1.5 atmosphere. What's the identity of the metal? All right. How do we find the identity of the metal? Well, there are 2 ways. If you know the atomic number, it's easy, right? Every element has a unique atomic number, but we don't have access to that. But if we can find the molar mass of that metal, then we stand a good chance of finding it on the periodic table, because the molar masses of most elements are significantly different from one another. There are a couple of places where they get really close together, which could be a problem. But this one is probably selected so that the molar mass is unique in the periodic table. So what we need to know is mass and moles. All right, we got the mass, 34.08 grams of metal oxide. We don't know the mass of the metal yet, okay? We do know something about the gas that's formed, the carbon dioxide. 4.37 liters of carbon dioxide. Is that right? 37? Yeah. At a temperature of 100 degrees C, which we might as well go ahead and add 273 equals 373. Okay. And pressure at 1.5 atmosphere pressure. All right. So we need to know the number of moles. Now, this is not the same moles as that. We're not there yet. This gives us the moles of the gas. And by stoichiometry, we can work our way back to the number of moles of this one. Okay? So, this means to be PV over RT. So pressure is 1.5. Volume is 4.37. R 0.08206. And temperature is 373. Okay, so the number of moles of gas will be 1.5 times 4.37 divided by 0.08206 divided by 373. So that's 0.214, yeah, 0.214 moles, 0.214 moles of CO2. Okay, so how many moles, how many moles of metal is that? Well, the ratio is 2 to 1. So for every one of these, there have to be 2 metals. So the moles of metal is times 2. 0.428 moles of the metal. Now we need to know the mass. Okay, let me see. How do I get the mass? Where is it? I didn't write it in there. The mass of the metal oxide is 34.08 grams. Okay. If we know the relationship of this metal oxide to carbon dioxide, let's see. I'm losing my train of thought. Oh, okay. Why don't we find out the molar mass of the metal oxide? We can do that really easy. We got moles and we got mass. So the molecular weight of the metal oxide is this many grams divided by this many moles. So that's 79.6. I think that's going to help us. Yeah. Okay. So where does this value come from? This value comes from a combination of that molar mass plus this molar mass. Does it not? 1 to 1. So the molar mass of the metal in there, remember how we determine the molar mass of a compound? We add the molar mass of each one of its elements. Right? So this is M0 or MO. What would be M? M would be subtracting the O from that. 3, 6, right? Yep, grams per mole. All right. So the molar mass of the metal is 63.6 grams per mole. So we go to the periodic table and say 63.6. So you just follow it along. It gets bigger from top to bottom and left to right. So you just follow it along until you find 63.6 or something really close to it. The closest I can get is copper. Our metal is copper. Okay, I'm running out of time fast. Let's see. Okay, let's do 86. '86 uses Dalton's law of partial pressures. Let's see, am I still on camera? It started drifting on me. There we go. 86. And here we are. So we've got a 142 milliliter sample of gas, but it's collected over water. So what's in that gas? Well, we're only interested in the gas itself, but collecting it over water does what? It infuses that gas with water vapor, right? So you have two gases in there. One is the gas we're interested in, and the other is water vapor. So we got to find a way to get rid of the water vapor from our measurement. All right, so the gas is collected over water at 22 degrees Celsius and 750 torr, 3 torr. What's the volume of the dry gas at standard temperature and pressure? All right, so let's see, what do we know? We know that the volume of the gas is 142 milliliters. Okay. We know that the temperature is, the beginning temperature is 22 degrees. Right, so the initial temperature is 22 degrees Celsius. We know that the pressure, the initial pressure, is 753 torr. What's a torr? 1 torr is 1 millimeter of mercury. So 1 atmosphere is 760 torr. So, and the vapor pressure of water at 22 degrees is 20 torr. So the pressure of water at 22 degrees is 20 torr. All right. So what does Dalton's law of partial pressure say? It says that the total pressure is equal to, in this case, the pressure of the water vapor plus the pressure of the gas. Okay. So did we measure the pressure at 22 degrees? Yep, 22 degrees. So this is the total pressure, 753 torr is equal to 20 torr plus the pressure of the gas. Like that. So now we can find the pressure of the gas at that temperature. But that's not the end of it, right? Because the question is, what is the volume of the gas at standard temperature and pressure? So that pressure is going to be what? 753 minus 20, which is 733 torr. Okay? So this is the pressure at that temperature. So the pressure of the gas at that temperature is 733 torr. Okay, so let me make some room here. We used Dalton already, so Dalton's done. Now we're going to use the ideal gas equation. You know, actually, we don't need the ideal gas equation because this is the before and after. We know the before conditions now. All we want to know is the after conditions. So this is initial. The volume doesn't change. The total volume doesn't change. 142 milliliter sample. Actually, that 142 milliliters is composed of two different gases. So that volume is not valid. What we've got here is this is the total volume. And remember, the all other conditions being equal, the volume of water vapor and the volume of the gas together equal that one. So actually we can approach this problem from two different directions. Either we can look at it as a volume problem or a pressure problem and then convert one to the other. But if we go with the pressure, then we've got to find out the relationship of volume. So we have P V over NT equals PV over NT. So this is initial, and this is final. So the pressure's changed, the volume changed, temperature's changing, but the number of moles, if we stick with the gas that we've now cleaned of its water vapor, then the moles are no longer there. So what's the initial pressure? The initial pressure for the gas is 733. You know, that's not going to answer our question. I think we need a different approach. Yeah, I think we need a different approach. Actually, we've got to include everything in this calculation. Pressure, volume, temperature. Pressure, volume, it's all there. No, we're on the right track. What do we need to find out? The final volume. The initial pressure is here of the gas, right here. The final pressure, I left out some things. The final pressure is 1 atmosphere, or 760 torr, because we're going for standard temperature and pressure. Okay. The final temperature is 273 K. The initial volume is 142, and the final volume is something else. Yeah, the final volume is different. But we do have the pressures. We need the pressures. Initial pressure, final pressure, yes, we're good. Okay, initial pressure here is 753. The initial volume is 142 milliliters. And the initial temperature is 22 plus 273, which is 295 K. The final pressure is 764. The final volume is our answer. And the final temperature is 273. Okay. There we go. if we solve for that, the final volume, it should be 128 milliliters. Now, why were we able to use 142 milliliters as our initial volume when that's the volume of the mixture? Because the water vapor occupies that volume and our gas occupies that same volume. I mean, even though that they're mixed, they still both occupy that same volume. The thing that changes is the pressure, right? Because in order to occupy that volume, this gas had to maintain a 733 torr pressure. And the water vapor, to occupy that much volume, had a 20 torr pressure. That's why we can use that as our initial volume for the dry gas. Okay. That was 86. Okay, I'm already past. Oh, I do want to do this one. Definitely do this one. It's another partial pressure, Dalton's law thing. 94. All right, 94. See if I'm still, yeah, there we go. 94. All right, what does 94 say? Right there. Okay, 94 says we have two bulbs, a 2-liter bulb with a gas at 1.8 atmospheres. Two liters, 1.80 atmospheres, connected to another bulb with a valve that's 3 liters. And inside there is a gas at 3 atmospheres. Is that right? 3-liter bulb in which the gas pressure is 3 atmospheres. There we go. Okay. When you open that valve, what's going to happen? This is the higher atmosphere pressure, right? So it's going to go that way until they're equalized. What we want to know is what's the equalized pressure? What's the final pressure when you get when everything settles down? Okay. So here's the thing. You've got a gas A and a gas B. If they're ideal, if they behave ideally, it doesn't matter what they are. But we can treat them as if they were different and find out what is the pressure of this one in the new volume. And then what is the pressure of that one in the new volume when you open the valve. So what's the new volume? It's 3 plus 2 is 5 liters. So the total volume equals 5 liters. And since Dalton's law of partial pressures is valid, then if we determine the pressure of this one in that volume and the pressure of this one in that volume, then you just add them together and you get the total pressure. All right, so we treat it as if this side is a vacuum, and when you open it, it redistributes itself in a new volume. Pressure volume, right? So pressure volume for this one, if we open the valve and that's a vacuum, then PV equals PV, 1 and 2. So initially, the pressure is 1.8 atmospheres, and the volume is 2 liters. What's the pressure when you go to 5 liters? Right? So the pressure for, I should say, this will be the pressure for B. What's the pressure of B when you open that valve? So that's 1.8 times 2 divided by 5 is 0.72. So the new pressure then is 0.72 atmospheres. And that's for B. How about this one? Well, it's going to be 3 atmospheres times 3 liters is equal to the pressure of A times 5 liters. So we have 9 divided by 5 is 1.80. 1.80 atmospheres. Right. So the total pressure is just the sum of the partial pressures. 1.8 plus 0.72 is 2.52. Which is C. That's your answer. Right there. Okay, I wanted to be sure and get that one out of the way. But I'm past time anyway, so it really doesn't matter. You have to watch the recording, some of you. But we're not done yet, unfortunately. I have several others. Let's move it back over this way. There we go. Several others that I want to talk about. All right, 95 is really simple. If you have these partial pressures in a mixture of gas, methane, nitrogen, and oxygen are these pressures, 135 for methane, 508 for nitrogen, and 571 for oxygen. What's the mole fraction of nitrogen? Remember how to calculate the mole fraction. The mole fraction is the ratio of the number of moles of the gas of the one component divided by the total number of moles. But that's also proportional to the pressure, the partial pressure of each one. So all we have to do is ratio the pressures, right? 508 for nitrogen, and then add them together. 508 for nitrogen plus 135 for methane and 571 for oxygen, right? Point 0.4, how many do I get? 3 places. 0.418. Okay? So that's why C is the answer. You have to recognize that the mole fraction can be calculated from partial pressures as easily as from moles. You don't have to know the number of moles, because gas is a gas is a gas. So the number of moles and the pressure are directly proportional, according to Avogadro anyway. Well, actually, Avogadro, he was interested in, Avogadro was pressure in moles. Yeah, so that solves the problem. Let's see, we're not going to stop for 96. Okay, 103. 103, here it is. Calculate the root mean square velocity for oxygen molecules in a sample of oxygen gas at 11.8 degrees Celsius. And there's your R value. This is a different R value. All right, what's the formula for root mean square velocity? Let's see, 103. It should be in your useful information, and I'll check to be sure. Just to be sure that it's available, because I don't expect you to memorize this one. There it is, bottom of the page. Square root of 3RT over molar mass. Square root of 3RT over molecular weight. And this is root mean square velocity. Is that correct? Yeah. They use a mu. Root mean square. Okay. So what do we need to know? We need to know R, it's given to us. We need to know temperature, which has to be in what? Kelvin. And we need to know the molar mass of oxygen, not in grams per mole, but in kilograms per mole. Right? Because kilograms is buried in this term right here of joules. See? There. So we have to have kilograms per mole. Right? So we got to do two calculations. First, temperature is equal to 11.8 plus 273, which is 284.8. Okay. And then molar mass for oxygen is 32 grams per mole. A 1,000 grams in a kilogram. Right? So it's going to be 32 times 10 to the minus 3, or 3.2 times 10 to the minus 2 kilograms per mole. Right? Now we can substitute this one right here. We can think this one is 8.3145, isn't it? Yeah, 3.145 right here. And temperature is this one. Take square root. All right. So we have that R times, and then temperature 284.8 times, and then divide by this value, 3.2 exponent divide, and then take the square root. So we have 471 meters per second. If you don't use kilograms down here, then you don't get the right value there. Okay, so C is the best answer out of that group. All right. Check my position there. There we go. Let's see. We should be getting close. Be sure and study the kinetic molecular theory of gases. That's number 109. I'm going to skip that one. Graham's law. You got to know what Graham's law says. Right? Graham's law is actually in the mathematical expression of Graham's law is in your in useful information. So it's the effusion rate of A divided by the effusion rate of B, is how fast is it moving, is equal to the square root of the molar mass of B divided by the square root of the molar mass of A. Okay. So this ratio is inversely proportional to the square root of the molecular weights. Okay, and you can take that square root and go outside. Just take the whole thing and go out like that. Right? That's a valid algebraic manipulation. Yeah, of course you have to get rid of these if you do that. Okay, that's Graham's law. Let's see. I don't want to keep too long or make this thing run too long, so let me see if this one is worth looking at. Let's see. Okay, this is a good thought problem, 116. You don't even have to do any calculations to answer this one. This is an application of Graham's law. So if you and your friend are in opposite ends of a hallway, and you have the hydrogen and your friend has the chlorine. So you have the hydrogen and your friend, I before E, and your friend has chlorine, and you want to form HCl exactly in the middle of the room, halfway between, or the middle of the hallway. Which is the following of true? And it looks like what they're looking for is who needs to release the gas first. Do you need to know the temperature to answer this question? No, not according to Graham's law, as long as the temperature doesn't change. Do you need to know the length of the room to answer this question? No, because we're halfway, right? It doesn't matter how long the room is. It'll just take a longer time if it's a longer room or a longer hallway. What if you release the gases at the same time? Where are they going to meet? Well, which one's heavier? Chlorine is a lot heavier than hydrogen, so hydrogen is going to move faster. This one's going to move a lot faster. So where would they meet if you release them at the same time? Over here somewhere. So what needs to happen? Well, your friend needs to release chlorine first before you do. And you time it, right? But that's not the question. It just doesn't need to be released first. Yeah. If you release this one first, it gets even closer to your friend. If you release this one first, then you can move that intersection point over here because it takes longer for chlorine to get to the middle of the room. All right. So that's why B's the answer. Your friend should release the chlorine first. All right. Let's see. Um, 124. All right. Remember at the end of the lecture, we talked about van der Waals corrections for real gases so that we can make the calculation and take those non-real effects into account. All right. So now we're going to look at these four gases: hydrogen, chlorine, ammonia, and oxygen. And assuming have enough information, we want to know which would we expect to have the lowest van der Waals correction. In other words, which one of these gases behaves most ideally. All right. So we need to look at several factors, right? Based on the ideal gas, we would expect the ideal gas to have a point volume, right? And interactions, minimum, okay? We can't say anything about temperature and pressure because that's not an issue here. They're all at the same temperature and pressure. So we need to look at the character of the molecules. Interactions, how do they interact and what size are they? Right? Well, which is the smallest molecule in this whole group? Hydrogen, right? Just look where it is on the periodic table. They tend to get smaller toward the top, right? Smaller toward the, let's see, size. I'm remembering the periodic. They get smaller as you go up and smaller as you go to the right. Right. So within a period. So based on what we know of these three gases, hydrogen would be the smallest. It would have the least volume, right? So it's a good candidate. The other thing we want to know is what affects interaction, right? Size and polarity affect interaction. Right? So polarity is due to polar bonds and geometry. So do we have any polar molecules in here? Well, hydrogen, chlorine, and oxygen are all uniform, right? They're nonpolar. Ammonia is polar, right? So it's out. It'd be the worst candidate. Then we look for size. The size of an atom or a molecule also makes a difference in the way it attracts, or the way it behaves, right? Because of London dispersion forces. The larger molecules have greater London dispersion forces. So if they're nonpolar, then we want the smallest molecule possible, right? Because the bigger the molecule, the bigger the atom, the more possible arrangements of electron density you can get, which means larger London dispersion forces. So again, the smaller molecule wins, and that's hydrogen. So hydrogen wins on two accounts: interactions and volume. So that's why the answer for this one is hydrogen. Okay, let's see if I've got any that really need to be. All right. Let's look at 142, and that'll be our last one. 142. This sort of pulls everything together. There we go. Oops, too far. There. 142. All right. Consider the reaction between ethane and oxygen, right, where it's a combustion, and it produces carbon dioxide and water. Okay, that's typical of hydrocarbons reacting with oxygen. What volume of carbon dioxide will be produced at standard temperature and pressure from a reaction of 4 liters of ethane and 7 liters of oxygen? All right. Okay, so we have to have a balanced equation first, correct? So we need ethane, C2H6, plus oxygen, yields carbon dioxide and water. Okay. So we need to balance that equation. Yeah, we better do a budget for this one. So we have carbon, hydrogen, and oxygen. On this side of the equation, we have 2 carbons, we have 6 hydrogens, and 2 oxygens. On this side, we have 1 carbon, 2 hydrogens, and 3 oxygens. See, did I get that right? 8, 10. 2, 8, 10. 1, 2, 3, 4, 5, 6. 3, 4, 5, 6. Okay. Now, if we balance the carbons first, we're going to leave oxygen till last, remember? So we have 2 carbons. That makes 5 oxygens. Okay? Now we can balance the hydrogens. We need 6 hydrogens. So we need 3 here to make 6 hydrogens. And that makes 3 plus 4 is 7. Okay? Now we can use oxygen to balance that. So we're going to have to use the fraction trick. Okay? 7 halves makes 7 oxygens. Right? Now we're going to get rid of that fraction. Times 2. So now we have 2 C2H6. See, am I walking again? Yeah, it's trying to. Plus 7 oxygens yields 4 CO2 plus 6 water. Now we have a balanced equation. Now we can say, what are we given? We're given 4 liters of ethane and 7 liters of oxygen. Okay? Remember, when you have exact amounts of reactants given, one of them is going to be limiting. Right? So, how do you do that? Well, since volume, as long as we hold the temperature constant, the volume and the pressure constant, then the moles are going to be related to, proportional to the volume. So we can do our, I used to say that you can't go anywhere in an equation unless you know moles. In one respect, that's true. But we can also do now that we know what gases, how gases behave, that we can do that conversion. The ratio here is also for volume as well as moles, as long as all other factors remain constant. So we can say for 4 liters here, the ratio to CO2, which is the question, right? What volume of carbon dioxide will be produced? So this is the question. If we go from 4 liters here to that, then we have 4 on top and 2 on the bottom. This is ethane, and this is CO2. So we have 2 times that is 8. So that's how many liters will be produced from all of this ethane. How about the oxygen? 7.0 liters. And we have 4 CO2, and we have 7. So 7 into 7 is 1 times 4 is 4. So which one's limiting? Oxygen. Oxygen runs out and produces 4 liters of CO2. That's the answer. 4 liters. Okay? All right. I think I've covered everything that I had marked. So this is Wednesday. You've got till next Monday, class time, well, actually Monday midnight, to finish the exam. And Monday during class, we're going to jump into thermochemistry. Look at quantifying heat that is evolved or absorbed during a reaction.